Let's look at the different types of rate information and what each of them mean. So we're going to do this with a graph of concentration versus time. And I mean, what we're looking at here, I have a specific reaction that we're going to look at, N2 plus O2 making 2NO. And my concentrations, which I've tried to put some that explicitly match real data on here, these are in micromolar, and my time is in microseconds. So I've got a pretty zoomed in version of this graph. So if right, these concentrations versus time, you're going to notice that it looks kind of familiar. If you can't figure out why it looks familiar, let me know and we'll talk about it. So I'm starting with O2 and N2. So I'm starting with only reactants. I'm starting with zero product. But as the reaction goes, my N2 and O2 concentrations go down and my NO concentration goes up. It looks like, right, this has the same kind of stoichiometry format that the reaction in the last video did. The quickness with which my NO increases, right, it looks like it's going up twice as fast as the other is going down because of that coefficient. So with this kind of data, so how concentrations change over time, the average rate is the rate over a range of time. So pick 2 points, so I've got, right, 2 points picked here. I'm going to do it for O2. So I'm on the blue curve. Change in concentration of O2 over change in time. Well, this looks like kind of like rise over run, right? You can get this, just the values from the graph. That the rate that I get here would be the rate of disappearance of O2. And it's an average over whatever that range of time is. If I want to know the rate at a specific moment, I would take a tangent line. So you would take a tangent to that specific point in time and then find the slope of your tangent line. So the reason that these are different is that as a reaction goes, the rate can change. It could slow down, speed up, or it could stay the same. We don't know what's happening, and we don't have enough information to figure that out yet. So all we can do is take the data we're able to collect, which is concentration over time, and then figure out either at a specific instant or over a range of times what is the rate of the reaction. So an example of how you might see this not in graphical form. So in the first 10 seconds of a reaction, the I minus concentration dropped from 1 molar to 0.868 molar. Calculate the average rate of reaction in these 10 seconds. So I've also given you a reaction, which is H2O2 plus 3I minus plus 2H plus, making I3 minus and 2H2O. So the only thing we know how to do is the definition of rate. The definition of rate and the average rate, those things go together. So the rate of the reaction is negative 1 over the coefficient in front of I minus, which is 3. Change in concentration of I minus over change in time. The change in concentration of I minus, that's given, and the change in time is given. So this is going to rely completely on making sure that we get that coefficient in there. So change in concentration of I minus, that's final concentration minus initial. And in the first 10 seconds, that just means time point 1 was 0 seconds. Time point 2 is 10 seconds. So I end up with negative 1/3, 0.868 minus 1, divided by 10 minus 0. And I end up with a rate of reaction of 4.40 times 10 to the minus third molarity per second. So follow-up question, What is the rate of change in concentration of H plus during that 10-second interval? So the rate of the reaction is the same in that 10-second interval. If we were to define the rate relative to H plus, the definition of rate relative to H plus is negative 1/2 delta concentration of H plus over delta T. And the delta concentration of H plus over delta T, that's what we've been asked to solve for. Rate of change in concentration of H plus during those 10 seconds. So the rate is the same numerical value from earlier. I just have a different coefficient when I'm relating it to the concentration of H plus. So 4.4 times 10 to the minus third molarity per second goes in for the rate. This is equal to negative 1/2 delta concentration of H plus over delta T. So the change in concentration of H plus over delta T is negative 8.8 times 10 to the minus third molarity per second. Here, we're not talking about the rate of the reaction. It wanted the rate of disappearance. So having the negative can't be avoided. So it's good that it's okay for us to have it here.